Okay, this is the first lesson in our unit on derivative rules, and what we want to do by the end of this lesson here is be able to find the derivative of a constant function, a polynomial function, or a radical function using these rules for finding derivatives, what we call the power rule, the sum and difference rules, and the constant rules. And we want to be able to use each of these rules either alone or in combination with the other rules. And then we'll take a look at how you can use the derivative of a function to solve a problem involving slopes and equations of tangents. And this using the derivative of a function to solve problems is something that we're going to be doing in every unit for the rest of the course. So let's just first recap what we did in the last unit. We looked in the last unit at being able to find the derivative of a function. And what did we say the derivative of a function was? Well, it represented the slope of the tangent or the instantaneous rate of change of that function at a particular point. And we also found the derivative function, which was a function that gave you the value of the derivative at any point that you wanted. And we did this by, if our function was f at x, the way we were doing this by the end of the last unit was we said, okay, if we want the derivative, f primed at x, we took the limit as h tended to 0 of f at x plus h minus f at x all divided by h. And this is just a variation of what we did throughout Unit 910. We found the slope of the secant to our curve and then took the limit of those slopes of secants as we moved our 2 points closer and closer together. There's an easier way of finding the derivative, and that's what we're going to look at now. So we've got these 5 rules that I talked about here. The first rule is if you have a constant function. So let's say your function is just f at x equals c, where c is just a constant, some number. This rule states that your derivative function, f primed at x, is always going to equal 0. So what exactly does this mean? Well, let's do an example here. If my function was f at x equals 5, my constant there is 5, this rule tells me that the derivative of this function is just 0. Now, does this make sense? Well, we can visualize what our function f at x looks like. If we imagine plotting the graph of this, x, y, what does the function f at x equals 5 look like? Well, it's a horizontal line. I'll do this in blue here. A horizontal line that passes through the point y equals 5. So what does our derivative represent, or what does it tell us about this line here? Well, it tells us the slope of the tangent to this line, or the slope of this line at any point. Well, if this is a horizontal line, what is the slope of a horizontal line? The slope is always 0. So our function, our derivative function, has to always have the value 0 at any point. So our derivative is constant, it's going to be 0. So the next rule is a little bit more interesting here. It's called the power rule. It says that if you have a function, f at x, which is x to some power, n can be any number that we want in there, there's a specific way of finding the derivative. The derivative, f primed at x, is, we keep the x the same. Okay, we still have the base of our power is still x. We take this number that appears up here in the exponent, and we bring it down in front as a coefficient. And our new exponent is going to be whatever we had before, minus 1. So let's say our function was f at x equals x to the power of 5. Our derivative would be, well, let's see, we take that 5 that's up in the exponent, we bring it down as a coefficient, 5, we keep the x the same. And then up here in our exponent, our new exponent is going to be 5 minus 1. So our derivative function is 5x to the power of 4. Now let's say we have a function here that is a constant multiple of some other function. So that would be something where we've got f at x equals some constant c times some other function, g at x. This rule tells us that our derivative, f primed at x, is going to be that same constant, c, times the derivative of that function, so g primed at x. Okay, so what does this look like? Well, let's say our function was 7x to the power of 5. Okay. So we've got a constant, 7, times our function, which is x to the power of 5. And we want to find the derivative. Our derivative, well, our constant multiple rule says that our derivative here is just going to be this constant, 7, times the derivative of this function, x to the power of 5. Well, what's the derivative of x to the power of 5? We know that from this previous question up here. We know that if we take the derivative of x to the power of 5, we get 5x to the power of 4. So the derivative of 7x to the power of 5 is going to be 7 times 5x to the power of 4, or 35x to the power of 4. These two rules are called the sum and the difference rules. So you use these rules when you've got some function, we'll call it h as a function of x, which is made up of two functions, f at x and g at x, that are either added together or subtracted from one another. Sum and difference rules tell us that the derivative, h primed at x, is going to be the individual derivatives, so f primed at x and g primed at x, either added or subtracted. So how is this helpful? Well, let's imagine we've got a function like f at x equals 3x to the power of 5 plus x squared. We can think of this as being two functions added together. We've got one function here, which is 3x to the power of 5, a second function over here, which is x to the power of 2. So we can take this derivative just by doing the derivative of our first term plus the derivative of our second term. So what is the derivative of that first term there, 3x to the power of 5? Well, we can do that using the constant multiple rule and our power rule. We've got our constant out front, 3, so our derivative is just going to be 3 times. And then we do the derivative of that function, x to the power of 5. 5x to the power of 4. Bring down the 5 as a coefficient, subtract 1 from the exponent. Then we add the derivative of that second term. So our second term there, x squared, what's going to be the derivative of x squared? Again, we're going to use that power rule. We bring down this 2 as a coefficient, we keep our x there, and then we subtract 1 from our exponent. So 2 minus 1 is just going to be 1. I don't know, so we can write a 1 there if we want. So we can clean this up a little bit here. 3 times 5 is going to give us 15x to the power of 4 plus 2 to the x. And there's our derivative function. So let's just take a look. Well, first off,